So we previously looked at the group of subatomic particles called hadrons. Today we're going to be looking at something called leptons. Now the thing that distinguishes, as we said last time, between hadrons and leptons is that hadrons consist of quarks. Leptons do not have any quarks in them. And the lepton that you'll be most familiar with is the electron. Now we all know that the relative charge of an electron is -1. And a property that you're probably not used to, we're going to call it the lepton number. The lepton number of the electron is +1. Now, previously we were introduced to the concept of antimatter. And remember that antimatter is the complete opposite of regular matter. It will have the same exact mass, but the charge and all the other properties will be completely opposite. So, the opposite or the antimatter of the electron is something called the positron. And this is denoted by this E plus because it has a charge of +1. And because it's an antimatter and it will have exactly the opposite of what an electron does, it will have a lepton number of -1. Now, typically, antimatter is denoted by just simply putting the word anti in front of the matter you're talking about. So you would typically call the antimatter for electron an anti-electron. But the positron has its own unique name because it's special, I guess. Now, I'm going to introduce you to a couple more types of leptons. The first one is called the muon. And the muon is simply a heavier version of the electron. So just like the electron, it will have a charge of -1 and a lepton number of +1. But the only difference is that the muon will have a greater mass. And just like the electron, the muon also has an antiparticle, and this time the antiparticle is simply called the antimuon. And we'll denote it by this mu plus, and we'll call the muon the mu minus. And just as you expect for any regular antimatter, the antimuon has a charge of +1 and the lepton number of -1. Now, once again, there's an even heavier version of both of these particles, and it's called the tauon. Now, I'm not sure if this is strictly on syllabus for all exam boards, but the tauon is exactly the same as the other two, except again, it's just another heavier version. So, as you would expect, it will have a charge of -1, a lepton number of +1, and its antiparticle, which is called the anti-tauon, has a charge of +1 and a lepton number of -1, as you would expect. Now, in certain processes called decays, there are certain quantities that need to be conserved. And one of the quantities that need to be conserved is something called weak interactions, which we will go over in another video. The lepton number must be conserved. Now, there are some decays. Let's say we'll look at something called beta minus decay. And in this case, a neutron gets converted into a proton and an electron. And in a decay like this, if you looked at the lepton number, well, the lepton number of a neutron is 0. It's 0 for a proton and it's +1 for an electron. So we can clearly see that the lepton number isn't conserved. So this led to scientists theorizing that this decay is not actually possible and there must actually be another particle emitted. And it's true. We have found out there is something called a neutrino that is emitted. And in this case, something called an anti-electron neutrino is emitted in order to conserve the lepton number. So let's look at the different types of neutrinos that exist. So first up we have the electron neutrino. And the symbol for this is just a V looking letter and a little subscript E. Now, neutrinos are massless and they have no charge, but an electron neutrino has a lepton number of +1. And just like all the other subatomic particles that we've covered over the last two videos, electron neutrino also has an antiparticle, and this is called the anti-electron neutrino. And it's the exact same symbol, except it will have a little line on top to denote that it's an anti-electron neutrino. And just like you would expect, it will have a charge of 0, because that's opposite to 0, and a lepton number of -1. And neutrinos are found simply to conserve the lepton number in certain decays. So let's say initially you had no leptons involved, so the initial lepton number is 0. If then you emitted an electron, You would also have to emit an anti-electron neutrino in order to balance the lepton numbers. And notice that neutrinos actually come in pairs. So for the electron and the positron, you'll get either an electron neutrino or an anti-electron neutrino. But for the muon, you will get something called the muon neutrino. And this is denoted by the same V symbol, but this time with a mu subscript. And just like the electron neutrino, it has a charge of 0, it's basically massless, and it has a lepton number of +1. And as you would expect, it has an antiparticle called the anti-muon neutrino, denoted by this V symbol with a subscript mu and a hat on top. And again, as you would expect, charge of 0 and a lepton number of -1. And you'd also have the exact same thing for the tau one. You'll have a tau one neutrino and an anti-tau one neutrino. And understanding the concept of neutrinos will be quite important when it comes to answering certain decay questions in your exams. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.